Hello, Accelerated Chemistry students. This is Mr. Spurk, and this is your Chapter 10, Section 1 notes all over the mole, a measurement of matter. So let's talk about chemistry and you. So have you ever thought about how much sand is in a sand sculpture or even just on the beach? There are many different ways to go about figuring this out. Counting these sand particles would just be ridiculous, right? You wouldn't sit there and individually count each piece of sand. So the question we need to think about when looking at a sculpture of sand or just at the beach, or when we're in chemistry thinking about atoms, we want to think about how we can convert among the count, mass, and the volume of something. So throughout chemistry, we'll analyze the composition of samples of matter and perform chemical calculations that relate quantities of the reactants in a chemical reaction to the quantities of the products. So you'll never be stuck like Patrick when he was just making a random guess, or maybe that was his educated guess at how many mattresses were actually in the mattress factory. We're going to be able to figure these things out and get an accurate count. So we need to talk about measuring matter. Apples can be measured in 3 different ways. At a fruit stand, we measure them by the count. At a grocery store, we measure them by weight or mass. And at an orchard, we measure them by volume. And each of these can be equated to a dozen apples. By count, 1 dozen equals 12 apples. By mass, 1 dozen equals about 2.0 kilograms of apples. And by volume, 1 dozen equals about 0.20 bushels of apples. So knowing how the count, mass, and volume of an item relate to a common unit allows you to convert among these units. So we actually have conversion factors, because 1 dozen apples is 12 apples, 2.0 kilograms of apples is 1 dozen apples, and 1 dozen apples is 0.20 bushels of apples. So we can use those equivalencies as our conversion factors. So we're going to be finding mass from a count. So what is the mass of 90 average-sized apples if 1 dozen of the apples has a mass of 2.0 kilograms? So the first thing we want to do is, like when we did conversions in the past, we're going to start with what we know. So we know that we have 90 apples. And if we remember from that last slide, there are 12 apples in a dozen, but we want the units of apples to cancel out because we want to end up with kilograms. So 12 apples is going to be on the bottom, and that's equivalent to 1 dozen apples. We're going to squeeze that all in there. So then we need to go use our conversion factor from a dozen apples to the kilograms of apples. And so we know that 2.0 kilograms of apples is about 1 dozen, or there are 2.0 kilograms of apples in 1 dozen apples. So we go back through and we can see what units cancel. So we can cancel this with this, dozen with dozen, and we're left with kilograms of apples. That's what we were looking to get. So when we multiply that all out, we're left with 15 kilograms of apples. So 90 apples is the same as 15 kilograms of apples. So you can see I wrote over everything that I was trying to say here, but like I had already said, we're going to use dimensional analysis like we've done in the past, unit conversions, and we're going from number of apples to dozens of apples to the mass of apples. So what is a mole? Recall that matter is composed of atoms, molecules, and ions. And these are extremely small, and they exist in an extremely large number, even in small samples of items. So counting particles one by one is not practical, much like counting sand on the beach isn't practical. So let's think about counting eggs. It is easier to count by dozens than by individual eggs, right? Because a dozen is equal to 12 of something. A dozen, like I just said, it's just the specified number of things. So now we're going to learn about counting with moles. So like a dozen, chemists have a unit that is a specified number of particles. The unit is called the mole. A mole, or abbreviated, is just MOL. So a mole of a substance is 6.022 times 10 to the 23rd representative particles of that substance and is the SI unit for measuring the amount of a substance. The number of representative particles in a mole, 6.022 times 10 to the 23rd, is called Avogadro's number. The term representative particle refers to the species present in the substance, usually atoms, molecules, or formula units. So it's basically just means how many pieces. For example, there's iron atoms, water molecules, H2 molecules, CaCl2, compounds or particles. Those are all just pieces. Just like we have a dozen eggs, we could have a dozen water bottles or a dozen people. Just representative particles. So converting between number of particles and moles, the relationship 1 mole is equal to 6.022 times 10 to the 23rd representative particles is the basis for the following conversion factors that you can use to convert numbers of representative particles to the moles, and vice versa. So as we see here, since they're equivalent, we can set these up as a conversion factor either way. So magnesium is a light metal used in the manufacture of aircraft, automobile wheels, and tools. So how many moles of magnesium is 1.25 times 10 to the 23rd atoms of magnesium? So here we're solving for moles and we're given atoms. So we're going from atoms to moles. So much like we did with the apples and like we've done in the past, we start with what we know. So we know that we have 1.25 times 10 to the 23rd atoms of magnesium. And we're going to use our conversion factor of 6.022 times 10 to the 23rd atoms for every 1 mole. So when we look at our units, we can cancel atoms with atoms, and we're left with mole on the top. And then when we solve that out, we get 0.208 mole, or moles, of Mg. So basically, we just figured out that 0.208 moles of magnesium is the same as 1.25 times 10 to the 23rd atoms of magnesium. So let's talk about the size of a mole. So although they share a name, the animal mole and the SI unit mole are obviously not the same thing. We can assume that an average animal mole is 15 centimeters long, 5 centimeters tall, and has a mass of 145 grams. So based on this information, the mass of 6.022 times 10 to the 23rd animal moles is 8.73 times 10 to the 22nd kilograms. The mass of Avogadro's number of animal moles is equal to more than 60 times the mass of all of the water in the Earth's oceans. If spread over the Earth's surface, Avogadro's number of animal moles would form a layer more than 8 million animal moles thick. So this is a huge number, and when we think about it on the scale of things that are normal size, like a mole, it's an incredible volume. But when we think about it compared to atoms or molecules, it's much, much smaller. So converting moles to the number of atoms. So propane is a gas used for cooking and heating. How many atoms are in 2.12 moles of propane? So we are going from moles to molecules to atoms. So we're going to start with 2.12 moles of C3H8. And we know that there are 6.022 times 10 to the 23rd representative particles per mole of something. So we can say that there are 6.022 times 10 to the 23rd molecules per 1 mole of C3H8. And now we want to go from molecules to atoms. So if we add up the number of atoms per molecule of propane, there are 3 carbons and 8 hydrogens. So there are 11 atoms per 1 mole of C3H8. So when we go through and we cancel out our units, we can cancel moles with moles, molecules with molecules. Sorry, this should be molecules here. And we're left with atoms on top. So when we multiply that through, we get 1.40 times 10 to the 23rd atoms. So there are 1.40 times 10 to the 23rd atoms in 2.12 moles of propane. So let's go back and talk about the mole and the dozen. So how are they similar? They are both quantities made of a specified number of representative particles. A dozen of something is 12 of that thing, and a mole of something is 6.022 times 10 to the 23rd of that thing. So now let's switch gears a little bit and talk about molar mass. So how do you determine the molar mass of an element and of a compound? So let's recall that the atomic mass of an element is expressed in AMU, or atomic mass units. So if we look in the column on the left, we can look at carbon atoms, and when we have one carbon atom, they have a mass of 12 AMU. And we can just see here, as we add more, our mass is going to increase, and same for hydrogen atoms. And then we can look at a mass ratio comparing the two. So the mass of a mole of an element. So the atomic mass of an element is expressed in grams, is the mass of a mole of the element. And the mass of a mole of an element is its molar mass. For carbon, the molar mass is 12.0 grams. And for atomic hydrogen, the molar mass is 1.01 grams. So these are just the same values that are on the periodic table, but now we're just calling them grams instead of atomic mass units. So if we look at this figure over here on the right, you can see that the mole, or 1 mole of different substances, is not the same volume or the same mass. 1 mole of carbon atoms is 12.0 grams, 1 mole of sulfur atoms is 32.1 grams, and 1 mole of iron atoms is 12.0 grams. The molar mass of an element contains 1 mole, or 6.022 times 10 to the 23rd atoms of that element. And the mole can now be defined as the amount of substance that contains the same number of representative particles as the number of atoms in 12.01 grams of carbon-12. So 12.01 grams is the molar mass of carbon. So 12.01 grams of carbon is equal to 1 mole of carbon atoms. 24.3 grams is the molar mass of magnesium. So 24.30 grams of magnesium is equal to 1 mole of magnesium atoms. The molar mass is the mass of 1 mole of atoms of any element. So to find the mass of a mole of a compound, you must know the formula of the compound. A molecule of SO3 contains that should be 1 atom of sulfur and 3 atoms of O, or oxygen. So the molecular mass of SO3 is, sorry, I didn't mean to click through that slide. So we can solve for the molar mass. So we have 1 mole of sulfur, and it weighs 32.06 AMU. And we add that to 3, because we have 3 moles of oxygen, times the atomic mass of oxygen. And when we add these up, we're going to get 80.06 AMU. Or now we know that we can change AMU, and it is equivalent to 80.06 grams. So this is the mass of 6.022 times 10 to the 23rd molecules of SO3. So the decomposition of hydrogen peroxide, or H2O2, provides sufficient energy to launch a rocket. What is the molar mass of hydrogen peroxide? So we're going to do what we did before. So we know that 1 mole of hydrogen is equal to 1.01 grams of hydrogen, and that 1 mole of oxygen is 16.00 grams of oxygen. So to start, we have 2 moles of hydrogen, and we need to convert that to grams. So we know that 1.01 grams of hydrogen is equal to 1 mole of hydrogen. So when we multiply that through, we get 2.02 grams of hydrogen. And when we do the same for oxygen, we have 2 moles of oxygen times 16.00 grams of oxygen per 1 mole of oxygen. Multiply that out, and we get 32.00 grams of oxygen. And so the molar mass, we just add these two together. So when we add these two together, we get 34.02 grams per mole of H2O2. And that's molar mass. So we made it through that PowerPoint here. And so as always, all information on these Google Slides has been acquired and adapted from Pearson Chemistry 2012 edition of the textbook resources, CD, and pearsonchem.com.